Awesome. I'm assuming that robotic voice means that we're good to go. Hello, everyone. My name is Michael Buford. I am the Vice President of the Von Braun Astronomical Society. Thank you for coming out to our very first show members meeting in over a year and a half, which is absolutely crazy. It has been so long, and I'm so glad to see so many new faces, as well as some old faces as well. Tonight, we have a very special program from Chuck Lewis. Chuck's going to be talking to us about Skylab. Since we're a little bit late already, I think we're just going to jump right into it. Are you ready, Chuck? Yeah. All right. So I'm going to hand the floor over to Chuck. Also, everyone, for the actual meeting, make sure that you get a ticket stub if you want to participate in the raffle. Okay, after the presentation, we'll just do it. But don't worry about it for right now.
So first of all, thanks for feeding me and watering me.
I don't think it's on.
I thought I hit share screen. Oh, okay. Share.
Are we on with Zoom as well?
1, 2, 3, 4.
There you go.
Okay.
We should be sharing the screen.
Everybody on Zoom can hear me as well? Good.
I should be able to.
Okay, this program is nominally titled Skylab's Astronomy, but the subtitle is really more appropriate. What some people will do for an image, and you'll understand that in a little bit, but I joined this organization a little over a year ago, and well, I was trying to figure, after a lot of procrastination, years and years of procrastination, I've always been involved, I've always been interested in astronomy, but not seriously until now. So in the process, looking around at what
I apologize.
5, 6, 7, 8. How's that?
Okay.
Jared?
We're good.
Okay.
That was
In the process of looking around at what I might want to get involved with, particularly with astrophotography, I realized how intense astrophotography was, and what some people would actually do to get an image. And a little bit after that, at one of the Zoom meetings, Don Martin asked me whether I was kind of introduced myself, and he asked me whether I was a beginning astronomer or experienced astronomer or whatever. I said, I'm a beginner. And after that, I began thinking, you know, can I really say that I've never been involved in any astronomy? Not true, because I spent a good part of my career dealing with and helping with Skylab, which was an astronomical tour de force, or at least for solar astronomy. So this notion of what some people will do for an image applied in spades to Skylab. And one of the things we'll do tonight is take a look at what some people did to get a solar image back nearly 50 years ago. And so we'll start with the first slide here. So Skylab was launched in 1973, and back earlier than that, NASA decided that they might be able to use some leftover parts from the Apollo program to build a space station. Skylab was really the first space station. It's not the one that we've got now, but it was kind of a precursor to it. And NASA called it Skylab. It used a leftover lunar excursion module. That's the LEM that you see pictures of on the lunar surface. And it also used a spare Saturn stage, Saturn S4B, plus a few new parts as well. And the idea at that point was to learn about living and working in space over long periods, and to do some real science as well. And solar astronomy was a major goal with that. And setting the stage for this back in the 60s, we'll show you this a little bit more detail in a minute. Wernher von Braun had long envisioned a space station. I remember seeing a lot of articles in Life magazine and that sort of thing back in those days. And along with that, the decision was made to cancel 3 of the lunar missions. That made some additional parts left over and available. And as well, NASA needed something to bridge that gap between Apollo and a real permanent space station, thinking about the International Space Station we've got today. And the other thing that was going on was that there was a period of active sun, which was imminent. Some of the early EVAs that were done on the Gemini program and some of the early Apollo programs left some doubt in some people's minds about how much work astronauts could actually do in space. There were some cases in some of the Gemini programs where the guys really expended an awful lot of energy flailing around outside. And as that focused in a little bit, it became clear to a lot of people that if the crew just had a foot restraint, it would make it a whole lot easier for them to do useful work. So bear that in mind, hold that thought for a minute. At that point, it was an unproven capability. And there were some other studies going on, the Apollo Applications Program and the Air Force's Manned Orbital Laboratory, all that. But here's a picture. This was an actual picture that Wernher von Braun drew. I think that's dated 1964. And it shows some early thoughts on his part about using some of the Saturn V components to build a space station. So that gives us a feeling that this was kind of in the back of his mind. So the result of it now is that we've decided to use parts left over from Apollo. Operationally, we consolidated the results of the Apollo Applications Program, MOLAB, and some other studies. And what Skylab would do was to validate the efficacy of VBAS in space. It would evaluate living and working in space. It would evaluate and establish the scientist-astronaut approach, where ultimately NASA would use not career astronauts, but scientists from the science community that would be trained to do astronaut kinds of things. And it would do real science in orbit with emphasis on solar astronomy, biomedical, and life sciences, and Earth observations. So here's what the Skylab cluster looked like, and we'll get into a little more detail here. And if I can use a pointer, the living quarters were an extra.
So I can see it. I can't see the pointer.
Oh, you can say, okay. Oh,
So I can
there
have
we go.
her.
All right, so Michael's going to try and echo my pointer for the Zoom people. Over here is the Saturn Saturn S4B module that's been outfitted as a habitation area. It was called the Orbital Workshop. There were a couple of solar arrays on each side. This is the nominal case now. There was an airlock module that was built especially for this. I'm sorry, that was, yeah, that's, you know, this is a multiple docking adapter. And the LEM that I referred to, lunar excursion module, was over here. And this is where the solar telescopes would be ultimately installed and used. This is the command and service module. The crew wound up attaching the service module, command service module, to the multiple docking adapter after they reached orbit. But in the meantime, just after launch, if you look at this picture, here's the workshop over here. Here's the LEM, we're not going to call the Apollo telescope mount. And at launch, it was launched in line with the rest of the major axis of the vehicle. Shortly after launch, it was winched over, pivoting on these trunnions right here. You can barely see a line. Kind of represents a winch that pulls it over at right angles. That opened up this port of the multiple docking adapter, so the command and service module could attach to that point. Here we go. So this is just a little quick explanation from John Eddy, Skylab Optics and Introduction. Now I'll read it for you because it's a little hard to read. For the first time in space, there were a few constraints on experiment weight, power, telemetry, or film storage. For the first time, solar astronomers were able to take advantage of photographic emulsions and long-term observational controls from space. For the first time, repairs and modifications were made on experiment equipment during the operational phase within Skylab and outside it during spacewalks by astronaut crews. And this way, the first crew salvaged the entire mission. Hold that thought for a minute. From there on, the 3 crews carried out adjustments, brought up replacement parts, and installed them. Tinkered, improvised, made changes, and generally worked as scientists do in a ground-based laboratory. Their effectiveness was beyond imagination. So this really is kind of a repeat of those original purposes that we talked about in a couple of previous slides. Back to the story about rescuing the Skylab by the astronauts. It's really another story for another day, but we talk a little bit about it and then go on to the rest of it. You notice in this, whoops. There we go. In this picture, you see only one solar array on the side of the workshop. The other one at launch was ripped off by aerodynamic forces on the way up, as well as the thermal shield that was wrapped around the whole thing. That almost caused the loss of the whole mission, but it also triggered a massive effort for about 10 days by both government and contractor organizations to first figure out what was going on, and secondly to figure out how to solve the problem. There were 2 fundamental issues. One of them was that with the loss of the thermal and micrometeoroid shield, it was really difficult to maintain the proper temperatures inside. This was important because we had food, we had medical supplies, and from an astronomical point of view, all of the film that was going to be taking all these wonderful solar images was sensitive to temperature as well. Now, one more thing about the film. This was far enough ago that we didn't have at that time CCD sensors or CMOS. Everything was using photographic emulsions. Most of these things were purchased from Kodak. Some of them for the solar scopes were in individual plates, some of them were on reels. And if you remember, if you've done any film photography, there's a thing called reciprocity failure. That means that the sensitivity of the film does not increase linearly with exposure time. That's a big advantage we've got with CCD and CMOS sensors now. But in any event, everybody was concerned about the internal temperatures. So that was problem number 1. Problem number 2 is that with the loss of that solar array on one side, about 40% of the expected energy source was not there. Ultimately, the crew, using some EVA techniques and the help of an awful lot of people on the ground during that 10 days, was able to erect the solar array. That's the one that you see there now, right there, and erect a temporary shield over the workshop so the temperatures could be stabilized. Before that, the thermal guys at Marshall and Johnson Space Center worked amazingly well to use the attitude thrusters to try and keep the temperatures reasonable. Interestingly, the first time I ever saw a digital calculator was when the Marshall thermal guys came down to a meeting that we had next to our workshop mock-up. And we were sitting around the table and they were trying to do fast calculations of the thermal properties and attitudes. And they brought out this Hewlett-Packard HP25, I think it was. It was the first one I'd ever seen. That was in 1970, about 1970, I guess. It's not hard to remember that because it was kind of interesting. We take it for granted now, but back in those days, it was pretty cool. All right, so ultimately we had 4 Skylab missions. This gets a little confusing because there are a lot of ways to count this. I used the one that I think is most appropriate. Skylab 1 was the launch of the Skylab cluster without any crew. This required a Saturn V, and it was launched on May 14th. That was the launch wherein we saw the loss of the one solar array, and that precipitated all this activity for 10 days. Skylab 2 launched about 10 days later, delayed by 9 days actually. And the crew for that was John Young, Joe Kerwin, and Paul Weitz. Skylab 3, and that lasted 28 days. Skylab 3, Al Bean, Owen Garriott, and Jack Lausma. And Skylab 4, Jerry Carr, Ed Gibson, and Pogue. And the backup crew for all of those was Rusty Schweikart, McCandless, and Story Musgrave. Some of those names you've probably seen many times in the ensuing years. Oh.
Did it
Can you
back?
hit the next slide?
Yeah.
There we go. What'd you do? Okay. He pushed the button. He said, touch the right button. All right. Make sure we get the right one. Okay. So let's talk a little bit about the telescope mount. This is the what's inside the lunar excursion module. There were 8 solar instruments on a cruciform optical bench, and I'll show some pictures of that in a minute. There are 2 X-ray telescopes, an XUV spectroheliograph, an ultraviolet spectroheliometer, ultraviolet spectrograph, visible light coronagraph, and 2 H-alpha telescopes. There we go. So this gives you a little feel for how this thing is put together now, and I'm going to use the cursor, and Michael can follow me here. This, perhaps you can recognize the lunar excursion module frame. This is kind of the guts of the limb. Inside that is a cylindrical core, which is really that X-shaped, that cruciform optical bench. This represents the 4 solar arrays that extended out from the limb. There was a door here, which was important to us in our little group, because this is where the crew would, this is the workstation for the crew for exchanging film canisters in 4 of those experiments. You can see the door here, there are a couple of handrails, and this picture doesn't show it, but there is a hand controller over on the right-hand side that allows the crew to rotate the cylinder to expose a different door, depending on which experiment he's trying to replenish with film. One of the interesting things here is these control moment gyros. We tend to think of gyros generally as a small instrument that gives us information back on attitude, which is then used to control thrusters. In this case, these control moment gyros were huge flywheels, and they managed to retain enough momentum that you could actually push on the axes and mechanically use those control moment gyros to react against to actually change the attitude over a small angular distance. Both of these things got saturated, that is, when they ran out of room to move in their trunnions, you'd have to use the attitude control thrusters to zero things out again. There were 3 of them. You only really needed 2 for all 3 axes. The third one acted as a redundant one. One of the challenges of those things in any gyro, any rotating mechanism in space is lubrication. I learned about this early on when I was working on this. In 1G, lubrication tends to be pumped around the axis of the bearing and keeps that film constant. But in 0G, it's much more of a problem. We ran into some of those problems, but that's another story too. So you can also see here, I'm trying to point out some of the things here that we can relate to doing the kind of astronomy that we do. Here's a star tracker. I guess that kind of relates to a guide scope. Over here, you could see the MDA and the service module. Experiment package is stuffed inside the LEM. And we're going to go to another slide here. Push the right button. Jared, you want to try it again? You got the magic fingers. Can you just give me the next one?
Yeah.
There we go. Okay.
We'll bring it back.
All right. So I looked these up. The system pointing accuracy of the scopes were 2.5 arc seconds and the X and Y coordinates and 10 arc seconds in Z. And then the entire cluster was accurate to 6 arc minutes in X and Y and 10 arc minutes in Z. Next one. All right, here you see the all of the telescopes installed in this this optical bench getting ready to be covered up with a thermal blanket. And the next slide. And here it is being inserted into the lunar excursion module. You can see one of the control moment gyros over on the right inside that truss. And the next slide. This is after it got into orbit, picture taken by one of the crews as they orbited. A couple of things to look at. This is one of the thermal shields that was added after they got into orbit with another EVA. Here's the solar array that was ultimately freed and extended. The sun end of the telescope, think of that as the objective end, is over here. And I didn't realize until I got looking at this picture for this presentation, this thing kind of looks like it's grinning at you and winking. I never noticed that before. Next slide.
No, you're good.
Try it. Try it.
Try it.
Try it again.
Hey, Chuck, what is that material?
Well, he's talking.
Which one?
Durable plant material. It almost looks like cardboard.
It's probably Mylar. I can't know. I don't know for sure, but I know the guys
Get it written down.
that developed that in, I guess it was Schwinghammer's lab, materials lab, worked pretty hard on, along with the JSC guys as well, coming up with the right thermal properties. They really turned out to be really expert. The only thing I remember about it is hearing those guys talking about emissivity over absorptivity as the measure of heat rejection capability, and they were always working about that, including paints that had the right alpha over epsilon. This is if you're talking about the surface of the shield here, that was just aluminum covered with probably that oh gosh, G13 or something like that paint that they were so fond of. Anyway, a couple of things to know here. Here's a set of foot restraints. We talked about foot restraints being sort of the key to effective extravehicular activity. You'll see a couple of open ports here. Those were really the objective portions of the cameras. There's a handrail here for the crew. Ultimately, the film needed to be replaced in 2 of these cameras, and that's what this set of foot restraints was for, as well as these handrails that help the crewmen get there. My job as a young engineer, I was about 30 years old, I guess, was to help develop the EVA accommodations that allowed the crew to make that film exchange. Our job we had kind of a maverick outfit, kind of like a Skunk Works, Marshall Skunk Works, I guess, in a way. our job was to be the interface between the flight crew and the detail designers. I always like to think of the detail designers at Marshall as having a lot of experience using 30, 60, 90 triangles and 45, 45 triangles, because that's what engineers do. But when you're talking about people involved in using those parts, you have to kind of throw those triangles away. So our job was to, I guess, provide some of the preliminary human factors requirements that help those detail designers satisfy what the crew needs were. We had guys working, as I said, on the EVA trail. We had another set of guys working on the control panel for the Apollo telescope mount, the human-computer interfaces there. Had some guys working on habitability issues. It was a wonderful time and a terrific group to be working in. So following up on that, this is a picture, probably my favorite Skylab picture. This is Owen Gary at a temporary, kind of an intermediate workstation. We had a set of foot restraints right down here that you can't see very well. He's at a point right on the edge of the thermal shield, of the solar shield, getting ready to accept a new pair of film cassettes that extended out to him on what was called a STEM. That stands for Storable Extendable Tubular Member, made by a company in Canada that made the robotic arm on shuttle and also on space station, Spire Aerospace. So this was our answer to how to get the cassettes out from the multiple docking adapter, or from the airlock hatch out to the crewman. Ultimately, this would extend out to where Owen could grab it. He would place it on, he would take that tree with the new cassettes on it, place it in this temporary storage area, swing around and get himself into the foot restraints, and then be able to make that exchange. And there's a picture of Owen. We lost Owen a couple of years ago. I guess Owen is probably, I guess most people would think of Owen as Huntstill's astronaut. Wonderful man. Really a terrific loss. So here's a picture of the lunar excursion module, showing some of the things we talked about before. There's an open door in the side of that cylinder. If you remember, we talked about that open space where the crew would get into position on those foot restraints and be able to make the film exchange. Right here, you see a pair of handrails. These help the crew get up over the edge of the sun end shield. Actually, the sun end shield is down here. So how did we manage to work on finding out where to place those handrails and foot restraints? Well, we used three major tools for simulation of zero-G. And one of them wasn't a simulation of zero-G, but it was a darn good ladder. We used 1G mock-ups, neutral buoyancy simulation, and KC-135 parabolic flight. Here's a picture, early picture, pretty soon right after I got into that group. You can see the, whoops. There we go. You can see the mock-up of the ATM with this open door area right here. And in this case, we're trying out a little different approach, and we had the test subject upside down in what's called a jump rig. It was really a 6 degree of freedom simulator that was suspended on a low friction support. So he was able to move around. It doesn't really simulate zero-G, but it does allow you to get into a lot of different positions for trying various approaches for doing things. And of course, at this point, we were looking at the best way and the best location for foot restraints, handholds, and that sort of thing. Here's a picture of the neutral buoyancy facility at Marshall. It's a large water tank. It's been decommissioned now, but it was 40 feet across, 75 feet deep, had 1.3 million gallons, and kept at a temperature of about 85 degrees. This is one of the early simulations we did, looking at trying out the various handholds and handrails that we developed. This is probably my friend Dick Heckman, who's also lives up here in the mountain, not too far away, maneuvering into that side hatch to try out the foot restraint positions and those other accommodations. This is probably me down here watching from that position. We also did some 1G simulation. This was a lighting simulation. One of the questions we had was whether the crew would be able to see inside the open doors to be able to place those film cassettes. We had alignment marks and a number of other aids that he'd have to be able to see into to actually line up the latches on the film canisters themselves. And you see over here to my left where this temporary storage was after it was placed there from his temporary location. And of course, we have the KC-135 zero-G aircraft, affectionately known as the Vomit Comet. You got about 25 seconds of near zero gravity. You can see from this little graph how that thing went. You'd pull up at about almost 2 Gs, 350 knots, go 45 degrees nose high, push over. The pilots would fly a parabolic trajectory, and during that time you had pretty close to 0 G. It depended on atmospheric conditions. You could get bounced around a little bit, and that didn't give you as clean a 0 G parabola as you'd like, but ultimately it got the job done. We used this simulation mode for validating some of those fine mechanisms, the latches and catches in particular on the film cassettes. They were all a little bit different, and we took some fairly high fidelity mock-ups up in those flights and made sure that that the suited crewmen could actually easily install them and remove them. One of the really neat things that I got to do was to share one of those flights we shared with the Johnson folks. They were getting ready to test some lunar. We're still in the middle of the Apollo program, and they were getting ready to test some 1/6G equipment. How many people have read Dune, science fiction story? Remember something called the thumper? It was used to call the sandworm. They had one on a lot of the lunar missions too. It would pound on the ground, and they were using that as a sort of a pseudo seismograph to investigate what the properties of the lunar soil would be. So I was fortunate to ride along on one of those, and yeah, I got a chance to experience not only 0 G but 1/6 lunar gravity as well. That's pretty cool. So one of the questions, I gave this presentation in a little different form back in the fall. One of the questions that they wanted me to discuss was, so with all of that serious stuff going on, what did you guys do to kick back and relieve stress? So this is going to be fun. We're talking about serious stuff so far, and this is going to be kind of funny. How many people listen to WLRH? Anybody listen to that? You remember years back, Judy and Harry Waters? Okay, Harry was our branch chief at that time. he was a wonderful man, very inventive, and a wonderful cartoonist. And so in the middle of all of this, we were looking for some way to relieve the stress, and they came up with this idea of generating the Bioastronautics Research Foundation, otherwise known as BARF International. And it's, I put it in sequence here because we just got talking about the vomit count, and it's kind of appropriate. So it was mainly an excuse for getting everybody together and going off and finding a place where we could enjoy our beverages of choice. So this is an example of a meeting announcement. This was a meeting at the NCO club at the Arsenal. And you can see the message there. When you get to the NCO club, give the Sergeant at Arms your name and tell him you're with the Bioastronautics Research Foundation. Don't say BARF, because you probably wouldn't get in. So along with this, we decided we really needed to have a BARF queen. And who did we choose but Phyllis Diller. So one of my jobs was as the BARF emetic was to do all of the correspondence. So I wrote Phyllis a letter and invited her to be our BARF queen. And she sent a nice one back, and I'll just read you part of it because it's tough to read. I can't tell you how complimented I am to be your queen, and I don't see why I have to give up my throne after 1969. Are you afraid my beauty might fade? Hang on, men. I'm not an ordinary BARF bag. I am weightless, shiftless, shapeless, Keplerian, and my G-string is clear down to D flat. I hardly ever get to Huntsville, but I was talking to Neil the other day, and he said the moon is a nice place to visit, but he wouldn't want to live there. So that's our queen. Phyllis died a number of years ago. Wonderful woman, but appropriately our BARF queen. All right, so I was a little concerned about this slide for obvious reasons, but Michael said put it in there, leave it. So we're talking about what people would go through for an image. This is one of the things we were also involved in our little group, and that was testing the waste management system for Skylab. So I'm going to try and maneuver my way through this without offending anybody. One of the things that happened was that in any meetings associated with this little challenge, everybody started out the meeting trying to use the biologically and appropriate terminology, but it got worse after about an hour in a meeting. So language kind of degraded a little bit. We were still serious about getting this done, but at one point we did have an opportunity to actually test that system in one of those KC-135 flights. And after I guess about a second. Yeah, and this was a difficult challenge because you had to be ready. You only got about 25 seconds of 0G, and you need to be able to do the job by the numbers. The lights would come on, the cameras would start, and it was kind of a competition between Marshall and Houston. They were unsuccessful. We managed to do it. And there's some stories that I'll tell you over beer someday, but ultimately it did get tested and it worked pretty well, and at least well enough to get by. But that goes again in the list of what people would do in order to get an image. All right, so back to serious stuff now. This is Ed Gibson at the ATM control panel. You'll see a lot of knobs and switches here. There was a tremendous amount of work that went into developing the ergonomics and the system, the human/system interfaces on this panel. It was not an easy thing to operate. They were trying to do simultaneous observations using all of those telescopes. And it took some training and a lot of good analysis to be able to do it right. You see right here, looks like an instrument on the surface of a CRT display. And what this really was kind of the equivalent of our live view capabilities. If anybody's doing astrophotography with a DSLR, you're probably going to use a live view camera, which lets you look at the image in real time. So this live view capability at that point gave them a picture of the solar disk in white light, zoomable views of the chromosphere, XUV, and the outer corona from the white light coronagraph. During the mission, there were a number of times where we had to develop some stuff on the fly to repair things that had failed. This is a pretty long mission, and things do degrade and deteriorate. This one I thought was interesting for this group because we can all relate to this. This is a filtered wheel on the SO54 X-ray telescope. Long around the third manned mission, it got stuck in one place, and the developers called and said, "We think we would be okay if we could move the filter wheel position to the open position." They would be somewhat limited in what they could do, but they could do a lot more with it in the clear position than with any of the filters in place. So they did some simulation back at their facility, and they decided that if the crew had a long screwdriver, they could push the screwdriver down through that whole elliptical window and lever the filter wheel to the new position. You can, oops. Here we go. Michael, you can follow me there. It's hard to see because this is kind of faint. This is the handle of the screwdriver. Screwdriver goes down through that elliptical window. It catches on the web below, and then the crew would be able to swing the handle in the upward direction and force that filter wheel back so it's centered under the opening. And there you see kind of the stack up of all the stuff that was underneath. So we had to push the screwdriver down through all of this, grab the tip of grab the web with the tip of the screwdriver, and managed to do it. We did this from that access area on the side of the limb. Got into the foot restraints, and had to do a lot of other things before it was ready to actually make that move. And just to show you the level of detail that we had to provide before sending up these procedures on the teleprinter, here's just a couple pages, 2 out of 10, with the detailed procedures. I'm not going to read it, you don't have to either, but you can see the kind of detail that we were working toward. You only get one shot at this, and the more you can, more information you can give the crew who've never seen this before, the better. So there was a certain amount of screwdriver preparation that had to be done to mark the depths so he could see whether he got the tip far enough down. This really worked pretty well. And whoops, ultimately, oh, I missed a slide there somewhere. Yeah, that successful EVA was a good way to demonstrate that the crew could actually exercise fine motor skills, even suited and with the visibility challenges and the restrictive nature of the suit as well. Okay, so just a couple of images here of some of the Skylab images. These are pretty hard to find because a lot of these things require a subscription to get some of the results. I was able to find these on the internet, and I'm just going to go through them quickly for you so you get an idea. Compare these with what we're able to do today and get a feeling for how far we've come. These were bright points in X-ray. You don't have to read the words, just kind of look at the pictures for a second. The loops in ultraviolet, solar prominences, a view of the solar chronograph. And one of the neat things that came out of this program was that Dr. Ciccone was able to get a Nobel Prize for developing really the field of X-ray astronomy, which started out with a lot of the stuff that happened on Skylab. So ultimately, Skylab's orbit decayed and it re-entered on July 11th, 1979. Michael, you want to come and tell us a little bit about some more details? You obviously have done some research on this. It's kind of interesting.
Sure, I'll just stand next to
Yeah,
Chuck.
yeah.
All right, so it actually landed in a very small town in Australia called Esperance. Now, Esperance is only about 15,000 people, and a local DJ in California basically was able to take the funds that basically Esperance gave NASA a $400 littering fine for littering Skylab on their continent and in their town, which NASA never paid. So in about 2008, a local DJ in Barlow or something like that. I know Barlow, right? But it was something like that in California. Barstow. I think it was actually Barstow, California, was able to crowdsource it, and they are now sister cities. They are twin cities, basically. So it became kind of an international big deal. I don't know like that word, but.
Oh, okay. All right, that's something I learned. All right, so ultimately, Skylab showed how we could live and work in space. It obviously validated the efficacy of VBAS and answered that question that was bothering everybody. Yes, indeed, the crew can do an awful lot, and with all of that, we were able to do an awful lot of maintenance work on Hubble, as you know. Spacelab took advantage of the scientist-astronaut approach, doing real science, using the astronauts as surrogate principal investigators, and we learned an awful lot about long-duration habitation in space. If it hadn't been for Skylab, all of those subsequent missions would have to have learned all that stuff all over again. So even though Skylab is kind of unfortunately kind of a lost child nowadays, it's amazing in retrospect what we learned from Skylab and how important it was. This little program is one way that we can go back and revisit that and remind ourselves of how important that mission was. So a couple of references I used for this. Leland Ballou, one of the bosses above me, many layers, built a really lovely report of Skylab. I got a lot of the information and pictures from that report. There's another source. It's a book written by David Hitt here in Huntsville, collaborating with Owen Garrett and Joe Curlin, published by the University of Nebraska Press, called Homesteading Space. I've got a copy of it over here on the table if you want to look at it afterwards. It's the nice thing about that book is that it is a really authentic version of everything that happened on Skylab. They interviewed a lot of the players, including me, to get the input from that book, and everybody I've talked to have said that what came out in the book was almost verbatim from the people that they interviewed. So it was, you can believe what's in that book. The other thing that I added here was this link to a documentary that's on YouTube that provides a little more insight into some of the things that happened during that 10 days I mentioned earlier, where everybody really got together and collaborated to save Skylab, which was a $2.2 billion program. And turned out to be one of NASA's shining moments. Anyway, that's my story. Ready for any questions? Yes.
What do they do with what do they do about humidity on Skylab? Because I know that was a problem with the early submarines, was that humidity short out all the equipment.
Okay, the question was, what did they do about humidity on Skylab? I think something I just read recently, they had to, one of the things for the film, they had to humidify the film because they were concerned about the film drying out during those periods when it got hot. And one of the approaches was to wet a towel, put it in the container with the film, leave it there for a little while. Some of these things, as far as the actual humidity, I really can't answer that. I know there were dehumidifiers as part of the environmental control system. While you ask that question, I'll just add something that's pretty interesting about the ECLS system. There was a series of blowers in the orbital workshop that circulated the air through filters. And one of the things that people hadn't thought of, but it turned out to be a no-brainer, one of those duh moments. If you lost something, a washer or a nut or something like that, just wait a couple days. It's going to show up on the filter because it's in 0G. It's just, no reason why it shouldn't be affected by the air currents, and the air currents ultimately will drive it toward the air filter. So if you lost something, wait a little while, go to the air filter, and you might find the part. Anybody else?
Chuck, was the film processed in space, or was it like I'm sure it wasn't full.
No, it was regular emulsion.
So
It was brought back. They had to bring it. Yeah, they brought it back in the command and service module.
Yeah.
They didn't know where to process it. So it was another one of those. You just a long delay, long wait to see what your data looked like, compared with what we can do today. Yes.
What was the mission duration back then?
The mission duration.
Yeah.
The first one was what, 28 days, and the third one was 100 and some days. It was
Well,
significant in comparison with what they had
Yeah,
done.
right. Yeah,
So I kind of set the stage for a lot of that
but
longer.
still, a month, a long time.
Yeah. Yeah, and back in those days, that was, until then, you had 2 or 3 day long missions. That was about it.
Oh, yeah.
Other than the lunar missions, but
3 days to the moon.
they were not in zero gravity, and everybody was wondering, what about the biomedical aspects of zero gravity?
Right.
And we ultimately found out that we need to worry about bone density, muscle loss, muscle mass loss. So in all of the subsequent missions, you'll see the crew exercising diligently to prevent that. Even on Skylab, we had a bicycle ergometer, which is kind of like a training bike. And the guys would get on that thing and pedal away just to prevent some of some of those issues. Anybody else? How are we doing on time, Michael?
Oh, we're good. Don't worry.
We're good? Okay, yes.
So, what about one of the things that they did was real science? You showed some pictures of the sun, but what did we learn about the sun?
I'm not a solar physicist. I wish I could answer that. I think with some of the things you can find on the internet, you could probably dig into that. Yes.
The film was in zero gravity, but which I should imagine it was different from gravity or not. But what about the gaseous atmosphere around it? Was it pressurized?
It was pressurized, yeah. It was pressurized, and we talked about
Yes.
and scrubbed for CO2, the CO2 scrubbers, and it was pretty healthy environment. What else can we say about that? A couple things about zero gravity to remember. In zero gravity, things still have mass. It still requires some effort to to move it against its inertia. So when you're moving something big in zero G, you can do it with a fingertip, but you got to wait a while before it starts to move, and then you got to decelerate it when you get close to where it wants to go. So it takes a little planning. You can move huge objects relatively easily, but you got to be careful that you start that deceleration before it gets where it's going. If you're a lot smaller than the piece that you're trying to move. So they have a chance to learn all that stuff. And you might recall seeing pictures of a couple of the guys running around the ring lockers on the inside, kind of doing a running on a track, except that the track is now in zero G, and it's like a rat running on a treadmill on a wheel. But that gave them some centrifugal force to hold them down against when their feet hit the ring lockers. They were able to go forward. Yes, Michael.
We have a question from Mike Worthy.
Hi, Mike.
He asked, Chuck, what was the orbital altitude of Skylab?
Can't tell you.
Okay,
It's another one to look up.
I'll Google it real quick.
Yeah, Michael's going to look it up. Okay. When you ask a question you don't have the answer to, you better admit it. Yes.
Did they bring any of the instruments back to Earth, or did they let
They had to leave. There's a limited amount of room in the command module. Unfortunately, they had to leave a lot of that stuff. They bring all the data back, but the instruments got burned up.
So
Don, Rob,
Skylab eventually came back to Earth. Did its journey last as long as NASA wanted? Or were there things that contributed to the failure so that it?
No, I think that's a complicated. It's a good question. The question was from Rod. Was the length of time that Skylab stayed up before its orbit decayed? I'll paraphrase it. Did NASA predict that time or not? I think they did. One of the thoughts was that by the time Skylab was going to start to decay, the shuttle program would be far enough advanced that the shuttle could reboost it if they wanted into orbit. As it turned out, shuttle program didn't get done early enough to solve that problem. So the partial solution to a safe deorbit was that they still had control of the attitude of the cluster using some of the retained gases in the RCS system, reaction control system. They were able to change the attitude to increase the drag at the appropriate time to try to get the cluster to drop down in an uninhabited area. They missed, obviously. They were shooting for the Indian Ocean, and they missed by a little bit. But you can't say that it was totally uncontrolled. They did have some control over that. Okay.
I already answered it for Mike, but it was 270 miles.
270 miles. Okay, there you go. Did that answer? You answered that, right? Somebody else?
No, it was Mike on the.
That's always Mike. Yeah. Okay. Good. Anybody else?
I had a question.
Okay.
He had a question. You go first. No, you.
I have one other question. It's kind of off topic a little bit. In your zero G flights, in your flight testing,
Yeah.
you have 25-second window. So I assume that you made several runs and you would fly out in March. How
Yeah.
many runs would you make in a mission, and how many such missions would you make over say, a week?
Okay. The question was, if you've got only 25 seconds of zero G during the parabolic flight, could you run your sequences end to end? I think I got your question right. And how many typically would you do? Yes, the answer is yes. You had to plan this. You had to divide your test up into 25-second long periods. It depends on what the objectives of the flight were. Some of those flights would go 15 parabolas, some would go 35, 40, 50. A lot of it depended on how well the people could do before succumbing to the willies. I could share a couple of interesting things with you. I was not good at this. I only made a couple of flights. I never did throw up, but I was not very useful after 5 or 6 parabolas. So I wasn't going to spend the government's money anymore. The thing to think about is that it's not the 0G that gets to you, it's the transition from 2 to 0 and to 0 to 2 to 0 to 2 to 0 to 2. And some people are just totally insensitive to it. The guy that was our 0G coordinator was totally insensitive to it. It just never did bother him. He'd be up there and just, he would grab people and throw them like a spiral football pass from one end to the other, spinning people around. And it never bothered him. On the other hand, there were some pilots that would not fly it. And the ones who did were in short supply. So a lot of times we'd get all set for a mission and they can't find a pilot. Or as you can imagine, this is a beefed up 707. So they had some issues occasionally with structural issues they had to fix. And, I mean, this plane was never meant for that kind of low load. What else can I tell you about that? The instrumentation for the pilots to do a perfect parabola was nothing more than a little fifth ball in a tube. Anybody fly gliders? No? Okay, some of the instrumentation in gliders is pretty simple. This is just a little light ball running up and down in a glass tube. It was sitting there on the panel. And all you had to do was push over and keep that ball centered in the tube. And these guys had their feet on the control panel and hauling back on the yoke because it took a little bit of effort to make those pullouts. It's really neat, really neat. They paid me to do this, right?
Chuck, did you introduce any special training to be able to work on Skylab that is not about ordinary?
No. That's an interesting question. Question is, did I have to have any special training to be able to get to do this? I got lucky. One of the guys that was already in this little Maverick outfit that I told you about was a good friend. And he had a race car, sports car, and I was one of the mechanics on his sports car. And we got to know each other, and he came in one day and he said, you might enjoy working on this little group because we're kind of operationally oriented, and I can see that you've got some operational talent. And one of the things he said to me that will always stick with me is something we have to worry about, that the flight crews have to worry about all the time, and not just them, but a lot of other people. In this business, you have to do things right the first time because you're probably not going to get a second chance. So kind of always had that in the back of our minds. And the people that were in this group were really diverse. When I got there, we had a bunch of mechanical engineers, aeros, a couple of electricals, a biologist, a psychologist, and a sculptor. So the diversity of thought in that really led to a lot of the out-of-the-box thinking. Don?
Yeah, what's your field?
Double E, electrical engineer.
Okay.
Yeah. Yes.
I've seen pictures of people on the trying to use using a electric drill drill, and the drill would go one way and they would spin the opposite.
Right.
Now, has anyone tried to develop one where they would make, I guess, a second motor that would spin the opposite direction?
Well, you
around
get either that or provide a reaction point that will keep that drill in place. It's a really good question. The question was, what about power tools and zero G? If you just took a regular drill and with a socket on the end of it and tried to spin the bolt, you would turn in the opposite direction and the bolt wouldn't move at all. So you have to have some way to react to that torque. And especially for Hubble, if you remember looking at some of the EVAs on Hubble, they used a lot of those power tools. And they had those kinds of ways to react the tool so that the crew didn't have to really muscle it. There was an awful lot of development that was done for that. And we took some hits as an agency. If you think of a lot of the stories about thousands of dollars for things on just on a regular airplane. But if you remember that the challenges are a lot different than they are here on the ground. Those tools have to be capable of being used by a guy in a pressure suit where his mobility is restricted, his visibility is restricted. You don't have gravity to help you. And anything that goes up in space has to have a history that goes along with it. If it's materials compliance and all kinds of safety hoops, wickets that it has to go through. But that all added to the high cost of getting all that done. More? Yes.
Whose inertial data system you use?
I don't. I sure don't. Okay, well, this has been great fun. I hope you enjoyed it as much as I did, and we'll have more to talk. A couple of memorabilia things on the table you might want to look at on the way out, or the time we have left. Thanks for inviting me, and we'll talk about that soon.
You got it, took out a leak.
Yeah.
All right.
Get that.
Well, thank you very much, Chuck. That was a fantastic presentation. If you have not picked up a raffle ticket and you are still interested in being in the raffle for Tom's lovely Frankenstein telescope that he has designed for us, please come get a raffle ticket. There's only a couple in there, and that will be very fun. Only a couple people. I'm going to put mine in there too. All right. We're going to go ahead and end the recording. Everyone say bye to the people on Zoom. Bye-bye. All right, close it out, Jared. Close it out.
No. Bad.
That's where I'm headed.
Okay. Stop share. And
Stop recording.
stop recording. Stop recording. Do you want to stop? Here's it.